for the first midterm. Okay? So that is happening soon too. One request from the CAs and the TAs who are grading the homework, we're letting it slide now, but as the semester progresses and the CAs have more demands on their time and the homework gets more difficult to grade, it's more and more important that you help us grade by, for example, only submitting problem 3 in the place where it asks for problem 3. So that means if you're preparing everything in one PDF, put in a page break before the beginning of problem 3 and select the pages that contain problem 3 when you submit. Even better, pull out the pages of the PDF separately for problem 3 and submit that. If you've got extra stuff on there, the tail end of problem 2 is at the top. The TAs who are going through this may not realize that you're writing about a different problem and may start grading it as if it were your solution to problem 3. 0, solved wrong problem. And then see your solution to problem 3 and says, we'll only grade one of the solutions you submit. And this is not out of malice, it's just we're flooded with stuff to do and they don't have time to think. So remember, first rule, don't make the other person think. So I've told the TAs that they are free to, for example, if you submit a PDF that is not legible, just to say 0, not legible, and move on. I've told the TAs that they are free, if they're overwhelmed, to say, there's extra stuff on here, I don't know what you want me to grade, 0, move on. So please help us by submitting what we want you to submit and nothing else. The second thing is there was some discussion on Piazza about office hours. And there seems to be a slight mismatch between the sense that you want more office hours and the fact that, with a couple of exceptions, not many people are showing up to office hours. So one reasonable hypothesis is that the office hour times that we've chosen conflict with other classes that a large percentage of you are taking. And so what we would like to do to try to get some information about this is when you go to lab tomorrow, tell your TAs, hey, it'd be really great if there were office hours here. And we can use that to tune exactly when we're offering office hours. So at least one of the TAs is already planning to shift their office hours around because to hit a time that we think is going to have fewer conflicts, judging by the number of people that show up to the discussion sections on Wednesday and Friday. The hypothesis is that time on Monday is probably pretty good. And some of the CAs are planning to start offering peer tutoring hours somewhat more sporadically because they won't want to do it on the weeks that they're actually grading. But watch the Google Calendar for that. And so we're going to try to respond as best we can, but we really need you to tell us what you need in a way that allows us to make reasonable decisions. And so when you're in lab tomorrow or when you're in lab on Friday, tell us what you would like. I think this is going to be more scalable than having a thread with 300 people voting on Piazza. I'm open to other suggestions for how to crowdsource this kind of decision. Are there any other admin questions? Yes. Right, so the protocol for submitting the homework. There's a group of 3 of you, you get together and you work out solutions for problem 1. For each problem, one person submits and then names the other people in their group on Gradescope. The other people could also submit, and as long as they also name the same group of people, it's not going to cause a problem, but this is asking for trouble, so don't do it. It could be one person submitting all three problems. It could be one person each submitting each of the problems. As long as one person submits the solution for each group, for each problem, the rest of it doesn't matter. Yes? Question? No, not NetID, Gradescope identity. You need to know who they are, who Gradescope thinks they are. Yes? So the Gradescope will ask for it in the submission form. The reason why we ask for it at the top of the PDF is occasionally things do go wrong, and we want a way to be able to recover in case someone makes a mistake and names the wrong people, or someone said, yeah, I was part of this group, I don't know why so-and-so submitted, I don't know why they put my name. But if their name's at the top of the PDF that was submitted, we go, oh, okay, we'll just fix that. Okay? So it's just a question of redundancy in case something goes wrong. And in a class this big, something will go wrong. Okay? So let's get started then. For the last week or so, we've been talking about finite state machines, how they work, what kinds of things they compute. And so far, we've just been thinking they compute yes or no. You give it a string, it's in some target language or it's not. How to combine them. So if you've got DFAs for simpler languages, you can combine them into DFAs for more complicated languages. And at the end of Thursday's lecture, I started talking a little bit about how you tell when building a DFA is impossible. How do you know that for a given language, there's no DFA that can represent this? There's a straightforward counting argument that implies that, in fact, most languages can't be decided by DFAs. And the argument is essentially the set of DFAs is countable and the set of languages isn't. So, in fact, almost all languages can't be accepted by DFAs. But that doesn't help when you're faced with a particular language. And so I started talking about this notion of a fooling set. A set of strings that certifies that a particular language can't be identified by a DFA because the DFA would require an infinite number of states. And there's no such thing as a finite automaton with an infinite number of states. It says so right there on the label. Okay. So I'm going to go back through this with some concrete details, and then I'll actually use this technique to prove that a couple of canonical languages are not acceptable by DFAs. They're not regular. And then I'm going to start working towards the proof that of this claim that I made last week, that a language is expressible by regular expression if and only if the same language can be accepted by some DFA. And in order to do that, I need to introduce a third type, a third representation called the non-deterministic finite automaton. So we'll start talking about NFAs today, mostly just giving a few elementary examples. And then Thursday, we'll walk through the actual proof. Okay, then it will actually take Thursday to do it because it's got a few moving parts. Okay, so let's start with this example DFA. This is actually the first DFA that we looked at last week. This is a DFA that accepts all strings of zeros and ones that represent a number divisible by 5 in binary. We designed this by writing out an algorithm and tracing out the states of the algorithm and building this nice little graph. But in principle, one might wonder if it's possible to do better than this. And so let me just write down a couple of strings here 0, 0, 1, 0, 1, 1, 0, 1, 1, and let's say 0, 0, 1, 1. Okay, now none of these represent numbers that are divisible by 5. The first one is 2, the second one is 31 and 27, and the third one is 3. They're going to end up in different places. But if you run the DFA for 0, 0, 1, 0, you'll do this. You go 0, 0, 1, 0, and you'll end up in state 2. Okay, so actually, let me undo that first. This ends up in state 2. If I run the same DFA with a different string, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1. Oh, it is divisible by 1. No, it's not. End up in state 4. Is that right? Something is wrong. What did I do wrong? Oh, I can't read my own DFA. Sorry. 1, 1, 0, 1, 1 goes to 2. Okay. That's what I thought I was supposed to do. Okay. And then finally, if I run the DFA on 0, 0, 1, 1, I go 0, 0, 1, 1, and end up in state 3. Now, none of these accept, but there is a sense in which I can distinguish the first 2 strings from the second 2, the last string, which is they end up in different states of the DFA. But I can't distinguish with this DFA the first 2 strings because they're going to end up in the same state. And one of the things this means is that if I add stuff on to the end of this string, see what would be a good thing to add on here. Let's add on a 1 to the end of the string. So 1, 1, 0, 1, 1, 0, 0, 1, 1. Okay, I glue on a 1 to the end of the string, I glue on a 1 to the end of the string. Because the first 2 strings led to the same state over on the left, I know without tracing through the DFAs with these strings that the first 2 strings on the right will also lead to the same state. Okay. In this particular case, because the first one is a binary representation for 5, I know that this is going to accept. And because I know that the first and second string on the right are going to end up in the same state, I know the second string is going to accept. So without converting the 6-digit number into decimal in my head, I already know it's divisible by 5. And then the last one, it turns out the last one is going to go to state 2. It's different. Okay. So the behavior of the machine imposes a kind of equivalence relation on the set of strings. Which strings lead to which state? And once I know that a given machine treats the 2 strings the same way, that as far as the machine is concerned, these 2 strings are equivalent, then no matter what I add on to those strings later, the machine is still going to treat those as equivalent. And in particular, no matter what I add on, if the first longer string is in the language, then the second longer string will also be in the language. If the first longer string is not in the language, then the second longer string is also not in the language. So there's a sense in which if the machine can't tell the difference between these 2 strings, then the language can't tell the difference between these 2 strings either. It's not as simple as just, are they both in the language or both not? The formal statement here is that if starting in state S, if I read string W, and starting in state S, I read string X,
then for all strings y, wy is in the language if and only if xy is in the language.
Okay? On the left, I'm making a statement about the machine, and on the right, I'm making a statement about the language. Now, if I look at the second pair of strings that I wrote up here on the board, let's, for the moment, just look at these two strings and their behavior over here. Now, the machine can tell those two strings apart, but that may be just an artifact of the machine. There might be other machines, other DFAs, where, in fact, that accept the same language, where those two strings actually do converge, in principle. But if I look over here on the right, and I say, oh, well, if I add a 1 onto that 5-bit string, it gives me a string in my language. It's a number divisible by 5. But if I add a 1 onto the second one, 0011, I get the binary representation of 7, and 7's not divisible by 5. So I can add on a 1 to those two strings, and the language can now tell those two strings apart, which now run this implication backwards. There is a suffix y that violates this if and only if, and that implies that this equation on the left, the two strings lead to the same state, is always false. It's false for every DFA. Okay? So say that I'm going to change my variable names. Z is a distinguishing suffix for two strings x and y if and only if xz is in L and yz is not in L, or xz is not in L and yz is. Okay, this is once I've fixed a particular language L that I'm thinking about here. So for this example, the string 1 is a distinguishing suffix for the strings 11011 and 0011. Because if I tack a 1 onto the first string, I get a string that's in L, and if I tack a 1 onto the second string, I get a string that's not in L. And if there is a distinguishing suffix, this implies that x and y lead to different states in every DFA for the language L. Okay. To say I've ever had a DFA where x and y led to the same state, that means I can't possibly distinguish them with suffixes later. Okay. So, in particular, this is a way of showing that a DFA has to have at least two states. I just say, here are a pair of strings. They're distinguished by this third string. So these two strings must lead to different states in every DFA. So this DFA must have at least two states. But now I can push this further and define something called a fooling set. So a fooling set F for L. I mean, F is just a convenient variable name, just like L is a convenient variable name for language. What it means for set F to be a fooling set, what this means is that for all x and y in F, where x is not equal to y, there exists a string z such that that's a distinguishing suffix. So xy in L if and only if, xz in L if and only if yz is not in L. Okay. This is the definition for a fooling set. So I'm going to start, to get this definition to sink in, I'm going to describe a fooling set for that language, binary strings that are divisible by 5. And I'm not going to walk through all the proof that it's a fooling set because it's, I have to check every pair. But at least let me show you what the fooling set looks like. So, for example, if L is binary multiples of 5, I could take the set F to be the string 0, the string 1, the string 0, 1, 0, the string 1, 1, and the string 1, 0, 0. I claim that this is a fooling set for this language of binary multiples of 5. And if I wanted to prove to you that this is a fooling set, what I would do is I would say, well, look, there are, let's see, 10 pairs of strings taken out of this set. 5 choose 2. For each of those 10 pairs, here is the distinguishing suffix. So just to give a couple of examples, if I pull out the string 1 and the string 1, 1, these are distinguished by the suffix 0, 1, because this is equal to 5, and this is equal to 13, and only 5 is divisible by 5. So the string 0, 1 distinguishes this pair, 1 and 1, 1. To give another one, maybe I'll let you figure this one out. Can anybody tell me a distinguishing suffix for this pair of strings, 1, 0 and 1, 0, 1? So, sorry? I heard two answers. 1, because it'll make the first string 5 and the second string 11. There's another choice. 0, because it'll make the first string 4 and the second string 10. Okay, so I could walk through every pair. One last sanity check. Let's look at the strings 0 and 1, 1. What's a good distinguishing suffix for these two strings? The empty string. This is something you'll hit over and over again. When I say, what's a good string? The empty set string is a string. So in this case, if I append the empty string to 0, I get 0, which is a multiple of 5, namely 5 times 0. If I append the empty string here, I get 3, which is not a multiple of 5. So just to drive home the point, I'll draw the little Greek letter there. And so for any pair, I can find some suffix that I can glue on to both strings in that pair and get one thing to be a multiple of 5 and the other one not. Now, hopefully it's fairly clear for this particular toy example how I came up with the fooling set. Yeah. Oh, okay. So an example that would not work. That's actually a good point. So let's say 1, 0, 1 and 1, 0, 1, 0. Okay, so this is 5 and this is 10. They're both in the string. They're both in the language. So there's a DFA up above the screen. They both lead to state 5. So I know that there's nothing I can do to tear them back apart again. But in particular, if I added, if I want to do this from base principles, if I added a suffix, let's see, I think the letter I'm using for this distinguishing suffix is Z. This would end up being 5 times 2 to the length of Z plus whatever the binary value of Z is. And this would be 10 times 2 to the Z plus whatever the binary value of Z is. So this part is divisible by 5, so if I'm thinking mod 5, I can ignore it. And so the value mod 5 of this string is the same as the value of Z mod 5. And the value of this string, again, is Z mod 5, and so they're either together or apart. Okay? Yeah. No, because I can't tell 0 and 101 apart. Because 0 and 5 are both multiples of 5. Yeah. Okay, good. Excellent question. Thank you, and on behalf of 150 other people in the room, thank you for asking the question. 2 points for the fooling set. One is, this is a proof that I can't recognize this language with fewer than 5 states. Because each of those 5 strings must go to a different state. Okay, so that DFA that I had at the beginning, this is in fact the smallest DFA that recognizes this language. Okay, that's nice. There's actually an algorithm that minimizes DFAs that's built on top of this kind of logic, that if you can find strings that distinguish between 2 states, then they're obviously different. If you can't find a string that distinguishes between 2 states, then you just merge them. The more interesting thing is if f is a fooling set for L, then any DFA for L has at least the size of F states. Now the interesting question. What if I could find an infinite fooling set for a language? Now, this particular language, this inequality means because I have a DFA that has 5 states, I can't find a fooling set bigger than 5. I'm not going to find an infinite fooling set for this language. But if I set up a different language, which I'll do in a second, and I'll show you an infinite language that has an infinite fooling set. And that'll be a proof that it's not regular. You can't build it as a DFA. You can't build it as a regular expression. Yeah, question in the back. If you can find a suffix that distinguishes the 2 strings, then in every DFA, those 2 strings lead to different states, and so they're not equivalent. But if you can't find a distinguishing suffix, it's possible that the strings really are equivalent at the language level, or it's possible that you have a DFA that sends them off in different directions, but later they'll merge, or you just have redundancy in your DFA. Yes? Here. I'm sorry? Where did the fooling set come from? Well, in this particular case, I think the argument is from the logic is from this formula here, that gluing on a bit string to the end of a binary number takes that number and multiplies it by 2, and then adds on a binary number below. And really, I'm just doing modular arithmetic, right? So what I chose as my fooling set are 5 different strings that have 5 different residues mod 5. 0, 1, 2, 3, 4. And that's why I needed 1, 0, 0, not 1, 0, 1. Okay. But this is an ad hoc thing for this particular language. When we start talking about more interesting things, there are a couple of rules of thumb for things to try. But at some level, it's you think real hard, and then you write down the answer. You follow? It could. So 0, 1 is a perfectly reasonable fooling set for this language. It's just not the largest one, right? We're trying to prove that something has lots of states. Bigger fooling sets are going to be better at that than smaller fooling sets. But yes, the empty set is a fooling set, trivially, for every language. Yeah. Okay, languages are sets, they have elements. DFAs are machines, they accept things. Languages don't accept things. Okay. So it's important to keep that distinction straight in your mind between the language as a sort of abstract set of objects and the machine, which decides whether you're in that language or not. And so the machine accepts or rejects. Yeah. I'm sorry, I'm having trouble hearing you. Could you repeat the question? In this particular language, no. So the question is it possible to take two strings that are in different states and by gluing on the same suffix, make them merge? Okay, for this particular language, because of the math here, the answer is no. But for example, if your DFA is looking for strings that contain a 1, then the string 11111 is going to lead to a different state than the string 00000. But if I glue on a 1, then they'll collapse. Yes? That is exactly right. So the definition of a fooling set means no matter which two strings I pull out, there is a distinguishing suffix. No, because, so the question is, what if I prove I can distinguish 0 and 1, and then I can distinguish 1 and 1, 0, and so on? But you haven't proved that you can distinguish 0 and 1, 0, so those might actually collapse. Those might actually be the same thing. You really have to say, no matter which pair you look at, you can tell them apart. Yeah. Good, so thank you. That's the next thing to talk about. Okay, so let me describe the canonical language. Okay, so this is the set containing the empty string, 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, and so on. Okay, 0 to the n, 1 to the n for all non-negative integers n. This is not the same as 0 star 1 star. The regular language 0 star 1 star means all strings of zeros followed by strings of ones. The stars are independent in a regular language. I can have 5 zeros and 28 ones. That's perfectly okay. For this particular language, string is in this language if and only if it starts with some number of zeros and ends with exactly the same number of ones. I claim that this language cannot be accepted by a DFA. Now, intuitively, the reason why I would expect that you can't accept this language by a DFA is think about how you would write an algorithm to decide whether a string belongs to this language. What would you do? You'd say, well, let's see, does the string start with 0? Great, okay, I can keep going, otherwise I would reject. And then how many zeros does it start with? And then when I start reading ones, I say, okay, how do I read the same number of ones? I do a comparison, and I either accept or reject. But notice, in order to do this, I had to remember something. I had to remember the number of zeros that I've read. I need a variable that can take on, in principle, an infinite number of different values. The short version of this is, I can't accept this language without being able to count. DFAs can't count, or they can count up to 5, or they can count up to 72 million, but they can't count forever. In order to accept this language, I really do have to be able to count forever. That's intuition, it's not a proof, but let's turn it into a proof. So let me describe a particular language here. I'm going to choose the fooling set 0 star. Now, I know people are going to ask me this, so for right now, I want you to imagine that this came down from Mount Sinai engraved on a stone tablet. Don't worry about where it comes from yet. Let's show that it's actually, this is the technique to solve every problem. Wait for a little bird to land on your shoulder and tell you the answer, and then prove that the answer is right. Okay? This is the little bird saying, it's at 0 star. Okay, fine. So I now need to prove that F is a fooling set for L, which means I need to prove that no matter which strings I pull out of F, something happens. So
I'm going to start the way I start every proof of a universally quantified thing. I'm going to declare, let these things be arbitrary objects. Be arbitrary, distinct strings in F. And then, so X and Y have a distinguishing suffix. So F is a pooling set for L. And here's my new language. Okay? So in order to prove that F is a distinguishing suffix, I need to pull out an arbitrary pair of strings and show that I can distinguish them. Now, whenever I declare an arbitrary object, it's helpful to think about what the definition of that object imposes in terms of what sort of structure can I assume about X and Y. They're not arbitrary bit strings. They're strings from that particular language. And because of that, I can say, oh, by definition of F, we have X is some number of zeros, and Y is some number of zeros. And because the two strings are different, those numbers are different. The length of X is a number I'm now calling I. The length of Y is a number I'm now calling J. I and J have to be different, otherwise it would be the same string. So I want to aim for, let's say, XZ is in the language, but YZ is not in the language. So the step that's missing in there is I need to show that some Z exists with this property, and the way you prove that is you say, here it is. Right? The way you prove a for all statement is you say, take an arbitrary one of those things and prove something about it. The way you prove a there exists statement is you say, here is a thing. Look, it has the property you want. So can somebody suggest a string Z that I can plug in here in the middle? Yeah. Okay, so let's let Z be 1 to the I ones. Now, if I do this, then XZ is equal to 0 to the I, 1 to the I, which is a string in L, because L is all strings that start with the same number of zeros as it ends with the number of ones. On the other hand, if I look at YZ, this is 0 to the J, 1 to the I, and this is not in L because I is not equal to J. So for this arbitrarily chosen pair of strings, X and Y, I found a third string Z that distinguishes them, that tells them apart. XZ is in the language and YZ is not. Because I did this for an arbitrary pair, that means this set F is in fact a fooling set for my language L. And now for the punchline, because F is infinite, L cannot be regular. Because what I just did is I proved that any DFA that accepts L must have an infinite number of states, one for each element of the fooling set. So it's not a regular language. And now, because it's not a regular language, I can stop wasting my time trying to build a DFA to describe it, trying to build a regular expression to describe it. I admit, okay, fine, I have to do something a little bit more complicated to recognize this language. And this is the point of fooling sets. Now, I do want to point out one thing about this proof technique. This is
one of the few times when I will say, so how would you prove that a language is not regular? And the response is not induction. There's no inductive hypothesis here. I just pulled out two arbitrary objects and I argued about them directly. Now, that's not a requirement. In principle, one could say, oh, well, let me pull out x and y, and now let me assume inductively that any string shorter than x and y in my language f have a distinguishing suffix, and let me derive a distinguishing suffix for those from the inductive hypothesis. But in practice, I've never run across a case where one needs to do that. So this is it. This is the entire proof. And when you're writing out the proof, I strongly recommend writing it out line by line by line by line. It's tempting to sort of write it narratively, just let the text flow. But again, because the graders have to grade a lot of these, it's very helpful to say, oh, look, you described your fooling set. Oh, look, you actually pulled out arbitrary strings. Oh, look, you told me what those strings are. You found a distinguishing suffix. You proved it's a distinguishing suffix, and then boilerplate, boilerplate, boilerplate. Okay? Yes? It doesn't matter. In this particular case, the fooling set is, in fact, countable, but that was a convenient choice. Right? I got to choose the fooling set. For this language, actually, it's pretty clear that there's a countable number of equivalence classes, just how many zeros start the string. That's not going to be true for other languages. So let me maybe go through another example. But the short answer is no, this is not a thing that matters. There are an uncountable number of strings, but it doesn't really matter. Okay. So let me define another language. I'll put suffixes on it so we're not confused with earlier things. This is the language WW reverse, where W is in my alphabet, some string in my alphabet. This is even length palindromes. Okay, I want to show that this language is not regular. And intuitively, it seems clear that this isn't regular, because if I'm reading that string one at a time, one symbol at a time, and I want to know whether it's a palindrome, I have to remember what all the symbols were in the first half of the string, so that when I'm reading the second half of the string, I can match them up. Which means I now need memory. I need to remember essentially an arbitrary string in order to tell whether I'm reading its reversal later. Okay? There's also the small problem of knowing where I switch from W to W reverse, but one problem is enough. And there's already a problem just, even if I told you, in fact, even if I put a special symbol in there, why not? I'll put a special symbol in there. Okay? So this is odd length palindromes with this in the middle. Okay, even though you get this signal saying, okay, I'm done reading the first half, I'm now going to read the second. Even here, in order to tell whether a string is a palindrome, I have to remember the entire string W. Can't do that with DFA intuitively. So, I want to prove that this language isn't regular, and so I need to come up with an infinite fooling set. And let me sort of brainstorm here. 0 star worked last time. Maybe 0 star will work this time. So, all right, let me try. If I had two strings of zeros like this, what could I glue onto these so that it would make one of the two in the language and one of the pair not? For this particular example, I'm just trying to do a sanity check here. Yeah.
So if I put pound 000, pound 0000, or hash, or sharp, or octothorpe, dear God, please know the name of the character is not hashtag. The thing that I added on to the end, that's a hashtag. Okay, okay, so it looks like if I start with two different strings of zeros, I can find a suffix that tells those two strings of zeros apart. So great, let's see if that works in general. That seems to be a reasonable idea. So, okay, fine. Let f be 0 star. Let x and y be arbitrary distinct strings in f. So x equals 0 to the I and y equals 0 to the j for some I not equal to j. And then I'm aiming for xz is an L and yz is not. So z is a distinguishing suffix. So f is a fooling set. So L is not regular. What should my, and again, once I've decided what my fooling set is going to be, everything else I've written here is just boilerplate. I'm setting up the proof, and now I need to do the one thing, which is pull a suffix out. So what should my suffix be? I have a string of I zeros and a string of j zeros. What should I add on that puts one of those two expanded strings into L, but not the other? Yeah. Sure, I could use 1 star. But let's dance with the one that brung us and see if we can make it work. Yeah. Hashtag 0 to the I. Okay, so then xz is in L because xz is 0 to the I hash 0 to the I. And yz is not in L because yz is 0 to the j, tic-tac-toe, 0 to the I. And that doesn't have the right form, right? This is all zeros. If I've got a palindrome and it's got exactly one octothorpe in it, the strings on either side of it, the suffix on the right and the prefix on the left have to have the same length, and they don't. So we're done. We have a proof. Yes? Formally, yeah, but at this point, you kind of know that. Yeah. Excellent question. How much harder would the proof be if we didn't have that hash in the middle? So let's try. Let's go back to our original language, WW reverse. All right, now, again, I'm going to go through the same kind of sanity check. Maybe 0 star works again. So is there something that I can glue onto the first string and the second one that turns the first string into an even length palindrome, but the second one not? Now, I want you to notice the second one is already an even length palindrome, but that's a coincidence. There are no hashes. So let's say sigma is just 0, 1. Okay. We're getting closer. So 1, 0, 0 doesn't, 1 and a bunch of zeros doesn't work because that's not even length. Okay, good. So if I glue on 1, 1, 0, 0, 0 to both strings, one of them is an even length palindrome and the other one is not. And it's hopefully clear at this point how I would do this in general.
If I've got 0 to the I and 0 to the J, I would add on 1, 1, 0 to the I. And it would turn one into an even length palindrome and the other one not. Now, the examples I'm showing you here make it look like I'm only ever going to use 0 star as my fooling set. So let me show you that that's not necessarily going to be true. And I'm going to leave out most of the boilerplate because it's all the same. Okay, so somebody already suggested 1 star. Can anybody suggest something else, something that hits slightly differently? And the way that I want you to think about this is when we added that 1, 1 and a bunch of zeros onto the end of the string, what we were doing was imposing structure. That 1, 1 served as the boundary between W and its reversal. In the first proof up there, again, we added that hash in front of the distinguishing suffix to impose that structure. We imposed it in the distinguishing suffix. We could also impose it in the fooling set itself. So I could let the fooling set be 1 star 0, 0. And now my distinguishing suffixes are all going to be of the form 1 star. This 0, 0, I'm saying, here's the line between W and its reverse. And I imagine when I'm thinking about designing the fooling set, this 0 is the end of W, that 0 is the beginning of W. And, well, I may put everything else 1s to make sure there aren't any other coincidences between what goes on the left and what goes on the right. Okay. I could also have done this. Okay, alternate between 0s and 1s and then have an extra 1. All right, now that means that if I'm looking at a particular example, here are 2 strings in my language. I'm writing this down in a way that everything is kind of and then there's something weird happening at the end. And that something weird happening in the end, again, I'm imposing structure here. I want this to be the signal that I should switch to the other half of the string. So in this case, my distinguishing suffixes are going to be of this form. Right? So they're going to be, instead of alternating 0s and 1s with an extra 1, it's going to be alternating 0s and 1s with a missing 1 at the beginning. Okay. So let me try another one. W, 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 where W is in, sigma star. So this includes strings like this. Now this looks even worse. I not only have to count, but I have to count and remember, then I have to remember it twice. I have to match things up. And this looks really horrible. Obviously, this is not a regular language, but can somebody suggest how we would prove that this is not a regular language? How would you design a fooling set for this? And this is the last one of these we'll do. You'll see more of these in lab tomorrow. Yes? Okay. So I'm going to let my fooling set be even length strings of zeros. So sanity check, I will write down 2 even length strings of zeros. What are you going to imagine as the suffix that distinguishes these? Okay. So in this case, you could do 2 zeros, but let me push on that a little. Here, I have one that's length 6, and the other is length 12. They're both divisible by 3. I claim that I can still distinguish these, just not by playing with the length mod 3. Right? The trick is that I need the same string, three copies. Now, with all zeros, I don't seem to have a natural place to draw that line, so I need to impose a place to draw that line. And the way that I'm going to do that is by writing down a 1, and then 6 zeros, and then a 1, and then 6 zeros, and then a 1. And then here, I've got a natural division of the string into 3 congruent copies. But if I put the same red suffix onto the second string, those breakpoints don't show up in the right places. Because I only have those 3 ones, they have to show up evenly spaced, 1 in each copy of W. And so if I've got one that's got too much to one side, it's not going to work. So in this particular case, there's nothing special about the strings having even length. 0, 0 star works perfectly well, but I didn't really use the fact that they were even length. So maybe I should just use 0 star. And since I know I'm going to be imposing those ones in the distinguishing suffix, maybe it would be, the proof would be slightly easier to write down if I actually included those ones in the strings themselves. And now if I'm given 2 strings x and y out of my fooling set, my distinguishing suffix is just xx. And it's somewhat easier to explain. Right? So for any fooling set, almost any fooling set proof, there are actually an infinite number of possibilities that I need to consider. One question that students often ask is, what about strings W that start with 2 ones? I seem to have only considered strings that have lots and lots of zeros and only a few ones. What about all those other strings in the language that have lots of ones and few or no zeros? I haven't thought about those strings at all. Why, is this really a proof? Someone have an answer for this? Yeah. It's an infinite fooling set. And one way to say this is I found an interesting part of L4 that has enough structure to it that it's easy to prove it's not regular. Any superset of that with the same repeating structure, I won't say any superset of that, but it's essentially, in effect, what I'm doing is I'm saying, let's not think about L4 directly. Let's think about this language instead. I'm going to take the intersection of L4 with a different regular language that imposes more structure. If this language, if L4 is regular, then this intersection is also regular, because the intersection of any 2 regular languages is regular. There's this product construction that proves that. Conversely, if this intersection is not regular, then L4 can't be regular either. And so this is a different way of proving things. Once you know something else is not regular, if you can get to that something else by combining the language I gave you with like intersections and products and unions and so on, you can use that to sort of get around the fooling set idea. But what this fooling set argument is doing implicitly under the hood is it's not considering L4 directly in its full generality. It's considering this very structured subset of L4, and that's enough. I don't have to write this down when I'm thinking about it, but that's what's going on. Yeah. Yes, I just need to show that there's an infinite fooling set. It doesn't need to be every fooling set. You don't need to consider every possible string in sigma star. You don't need to consider every possible string in L. You just need to find an infinite set where every pair has a distinguishing suffix. Okay? Other questions about fooling sets? Now, if you go online, you go on Wikipedia, or if you wander over to Mahesh's course, there's another thing that people use to prove that languages are not regular called the pumping lemma. The pumping lemma says, don't write this down. I'm not writing this down. I won't ask you to use it. The pumping lemma says that if a language L is regular, then there is an integer n such that for all strings W of length greater than n, you can write W as the concatenation of three strings x, y, and z, such that for all I, x, y to the I, z is in L. Got that? So if you go out on Google and say, how would I prove this language is not regular, you're going to hit a lot of pumping lemma proofs. Okay? If you can correctly and successfully apply the pumping lemma, great. I can remember it because it was bounding to me 25 years ago when I was a student. The thing about pumping lemma is, first, it's harder to understand. Second, the proofs are harder to come up with. And three, passing the pumping lemma doesn't mean that your language is regular. Whereas there's a theorem that says, if there is no infinite fooling set, then the language is in fact regular. It's an if and only if. So if the language isn't regular, there is a fooling set proof. But there may or may not be a pumping lemma proof. And this is why we don't do the pumping lemma. But if you're confused when you go out on Google and see that other people are learning the pumping lemma, it's a great if you want to play around with it, but I've never seen a case where it was easier to apply the pumping lemma argument than the fooling set argument. Okay. All right. Other questions about fooling sets or proving things aren't regular? Yes. This is an excellent question. So if I've got two languages over, say, the alphabet 0, 1, and somehow you can show that they both have fooling sets of size 10 and no smaller, and in fact, here is the same set of size 10, and it's a fooling set for both languages. Does that mean that they're accepted by the same DFA? Are they the same language? The answer is almost. I believe what it means is the two languages are accepted by DFAs that have the same states and the same transition function, but they may have different accepting states. So the fooling set says these two things must lead to different states, and that's going to be true in both cases. But whether those states are accepting or not may be different between the two languages. So binary strings divisible by 5, we've seen the five-string fooling set. Binary strings that are equal to 1 or 3 mod 5 has exactly the same fooling set. And the DFA looks almost exactly the same. You just choose different accepting states. Yeah. So whether there's an intuitive way to do this depends on whether you think arguments about extending functions from individual strings to equivalence classes is intuitive. With a certain amount of mathematical experience under your belt, yes. This is something called the Myhill-Nerode theorem. There's a proof in the notes that, in fact, the minimum size fooling set is equal, the size of the largest fooling set is exactly equal to the number of states in the smallest DFA, which is exactly equal to the number of equivalence classes for this distinguishing suffix relation. And in fact, the minimum DFA is unique. It's uniquely defined by those equivalence classes. We have enough to do that we're not going to push on that this semester. Okay, so I have enough time to tell you what an NFA is. And I'm going to do this basically by giving an example, stating some definitions, and then we'll have to play with this more on Thursday. Okay. This is an NFA. It looks like a DFA, especially if you're in the back of the room, because you see circles and the arrows have labels. But if you look closely, you'll notice a couple of weird things that make it not a DFA. One is that this state on the left has two arrows leaving it labeled 0. I have a choice. When I see a 0, do I stay put or do I go up? The state at the bottom doesn't have an arrow labeled 0. If I'm in this state and I get a 0, apparently the universe ends. I have nothing to, I don't know what to do. Okay, so this is an example of an NFA, a non-deterministic finite state automaton. The reason why it's called non-deterministic is that the string that you feed it does not determine the next state, the sequence of states that you traverse. So if I start over here on the left and I read 0, 0, 1, 1, I might go 0, 0, 1, 1 and accept. I might go 0, 0, 1, 1 and accept. I might go 0, 0 and then die. Okay. I might go 0, 0, 1, 1 and in a non-accepting state. Okay. So NFA accepts a string W if there is a sequence of transitions going, say, from S to Q1 to Q2 and so on up to QL, where QL is an accepting state labeled A1, A2, A3, AN, where A1, A2, up to AN is just W written out symbol by symbol. And if it is possible to walk from the start state to an accepting state, where at every step I consume a symbol from the input and I cross an arrow that has that label, then the NFA accepts. So I have choices for how I walk through the graph. Okay. This is what I mean by when I say it's non-deterministic. The string doesn't determine the sequence of transitions, and in particular, the string doesn't determine which accepting state, if any, my sequence of traversals lands in. Okay. Now I can give a more formal definition here, and I have to. So an NFA is a tuple, just like, it looks a lot like the way you would formally write down a DFA. All right, so sigma is the input alphabet. Input with an N, just like union with an N. Input alphabet. Q is a set of states. Again, both of these sets are finite. S is a start state. So this is an element of Q. A is a set of accepting states. And now delta, the transition function, is a function that takes a state and a symbol, but instead of returning a single state, the one thing you must do next, it returns a set of states. 2 to the Q, this is standard notation for the power set of Q. This is the set of all subsets of Q. If Q has n elements, then 2 to the Q has 2 to the n elements. That's why the notation makes sense. Okay. And then I can extend this to a
a language that takes
extend the transition function. Instead of taking a single symbol, I can take an arbitrary string. And this more or less goes the way you think. If the string is empty, then the only state you can end up in is the state that you started with. And if the string is non-empty, you take all possibilities for what you can do with the first symbol, and then you for each of those, you consider recursively all the possibilities you can get to with the rest of the string. So if I write this down formally, Q star of little q w is either the set containing Q if W is empty. Otherwise, it's the union over all states that I can get to in one step of all the states I can get to from P with the rest of the string. Sorry, not of Q. If W equals AX. Okay? Okay, blah-de-blah-de-blah-de-blah. This means what I wrote in black up at the top. Okay. Now, we will have to think about this formality on Thursday when we do the equivalence, so it's useful to imagine what's going on. So let me take a particular string here, 0, 0, 1, 1, and I'm going to name these states S, 0, 1, and T. And I'm going to walk through what happens when I read off this symbol, these symbols in a row. Okay, so I start off in state S, and then I read the symbol 0. Now, in this picture, I have arrows labeled 0 from S to itself and from S to state 0. So that means delta of S comma 0 is the set S 0. Okay. Now, from here, I again read the symbol 0. Now, from S, I can get to either S or 0, and from 0, I can only get to state T. Okay. So, delta star of S 0, 0 is S 0 T. Now I read a 1. From S, I can get to either S or 1. From 0, I can't go anywhere. And from T, I can only go to T. So delta star of S 0, 0, 1 is S 1 T. And then again, delta star of S 0, 0, 1, 1 is also S 1 T. And now, because this final set of states contains an accepting state, the machine accepts the string. Okay? So, what I've done here is, instead of saying, let's think about, is there a sequence of transitions that starts at S and ends at some accepting state? Essentially what I'm doing when I'm walking through this logic is I'm saying, okay, I know at the beginning I'm in S. After one step, I don't know where I am, but I know I'm in one of 2 possible places. After the second step, I still don't know where I am, but I could be in one of 3 possible places. After the fourth step, again, I don't know where I am, but I could be in 3 possible places. And one of those places happens to be an accepting state. So in that case, I will accept. Yes? I could do the same thing with the DFA, but I want you to notice, what is the language that this NFA accepts? Right, strings that either have 2 zeros in a row or have 2 1s in a row. Now, a DFA for this language is not too hard to construct, but it'll have 6 states. Right? the freedom to sort of say, one of these, as long as one of them works out, we'll be happy, allows you to be much more compact. And in particular, we'll see this on Thursday. There are examples of languages where the smallest DFA for the language is exponentially larger than the smallest NFA for the language. Right, you pay for that compression by having a more complicated acceptance criterion. All right, that's it. We'll see you on Thursday. Please don't forget to talk to your TAs in the lab about office hours. Thanks.